Thank you very much. Okay, so now you understand why I didn't supply my title. It's too long. So like everybody, I would like to thank the organizers for the invitation and the opportunity to present this work. It's always a pleasure to be in Vienna and in particular at the Schrödinger Institute. So the work I will present is done together with my graduate student, Patrick Pench. And what it is about is the following. Now, it's about time evolution of operators in Lindblad equations. And to set the stage, I'll talk first a little bit about unitary time evolution in many particle systems. Okay, so as everybody knows, if you have a free theory, the equations of motion for operators are linear, so you can solve them exactly. So let's say if you have spinless fermions, Cj, you can solve the equation of motion and you can exactly compute these functions Fl and Gl, which tells you what these operators look like at any later times. And because it's a free theory, so you have a Wick's theorem, if you wish, then all other operators follow from what you have here. Okay, so in free theories, you can work out fully if you are given an operator at time t equal to 0, what the operator is at later times. Now, in interacting theories, also, as everybody knows, it's infinitely more complicated because if you write the Heisenberg equations of motion for operators, let's say a string of C daggers and Cs, then on the right-hand side of the Heisenberg equation of motion, you have the commutator of the Hamiltonian with the operator, and then you generate operators involving more of these Cs and C daggers. Yeah, and so you get an infinite hierarchy. So that's the Bogoliubov hierarchy. And obviously, this is very complicated, and it's not practical, for example, to work out what these operators look like at late times. Very complicated. Now, however, something in many systems, operators should look simple at late times, or certain operators should look simple at late times for the following reason. So this goes under the words of hydrodynamic tails in diffusive systems. So here's a cartoon of that story. So let's say we have a model with a conserved charge. So let's say its particle number is conserved. Then you can write the equation of motion for the density of that conserved charge, and that will take the form of a continuity equation, where on the right-hand side you have the lattice version of the divergence of the current. Okay, so now if you coarse grain, so you basically take these equations of motion and Fourier transform them and then focus on small momentum modes, you can turn this into an equation for a coarse-grained particle density and a coarse-grained current, which looks like this. And then in diffusive systems, the current, or the expectation value of the current at late times has an expansion which is related to the variation in the density itself. And if you plug this back in here, you basically get a diffusion equation for the density. And from that, you can infer essentially there must be a series of slow operators, so operators who decay very, very slowly at late times, because you obtain their dynamics from the diffusion equations. And for example, these ones here should do so. So these have in a sense, simple dynamics at late times. So they decay very, very slowly with some power law. And, but they're very special operators, if you wish. And so what you have to do if you have a particular operator you're interested in, because you're doing experiments and you measure some particular expectation value or correlation function, what you have to do is you have to project the operator you're interested in on these slow operators. So you basically have to compute the overlaps. And this is a very difficult and, in general, unsolvable problem. Yeah, so that's a cartoon of why the problem of hydrodynamic tails or hydrodynamic projection is still unsolved in general. Now, what I will talk about here is if you look at dissipative dynamics, so if you look at Lindblad equations, there exists a class of theories which are basically in between free theories, so they're not free, and fully interacting theories where you have a full BBGKY hierarchy. And for these dissipative systems, you can solve this problem of hydrodynamic projection exactly. So they're closed form expressions for hydrodynamic projection, and that's what I want to tell you about. Okay, so that sets the stage. Now, let me give you a little bit of background about what kind of Lindblad equations we're interested in. So we have already seen this yesterday, so I kind of can skip all of this, basically. So the Lindblad equation is an equation for the reduced density matrix of a system that is coupled to an environment. The environment is Markovian, and the time derivative for the reduced density matrix, of the system has a Hamiltonian part where you can, okay, so this describes unitary dynamics in the system degrees of freedom. And then and it also actually contains some parts that are induced from the coupling to the environment. So that's why I call it effective Hamiltonian. And then you have the dissipative part, which is coached in terms of these jump operators, which describe the coupling of the system to the environment. And this particular form ensures this, as we heard, is a completely positive trace-preserving map. So if you start with a density matrix, it remains a density matrix. Now, this is very general. In this talk, I will focus on a particular setup. So I will have a system which I will take, even though many of the things I'm going to say also hold in higher dimensions, but I will take it to be one-dimensional. So I have a one-dimensional chain of sites, and on that sites, I will consider models of spinless fermions. Again, you can generalize this a little bit, but so this is what we've done. And then the environmental degrees of freedom I will take to couple across bonds. Yeah? So the jump operators basically will act on each bond in the geometric way I have described here. And if I rewrite this Lindblad equation for this kind of setting where I, in addition, assume everything is homogeneous, yeah? So I will consider translation invariant system, again for simplicity. Then the Lindblad equation takes this form where I have one free parameter, which is this rate gamma, which is the strength of the dissipation, and these jump operators act on each side of the system, or on each bond of the system, okay? So that's the geometrical setup. So now I'm not interested really in the reduced density matrix. I'm interested in operators. So I want to go from the Schrödinger picture to the Heisenberg picture. So this is completely standard. You can write just in exactly the same way as you can write the equation of motion for the density matrix. You can write the equation of motion for time-dependent operators. Here, the time evolution is induced by what's called the dual Lindbladian, and it takes this form here. And so it's very similar to the Lindbladian itself. Okay, so this is a very difficult problem still. You disagree? I'm surprised. You're surprised by what? You're going ahead already. So just okay. You're too fast. Okay, so let me come to this. So now we impose two requirements. I will take the Hamiltonian to be very simple. I take the Hamiltonian to be quadratic in fermions. Yeah. So the Hamiltonian part is a free theory. But now the jump operators, I take quadratic in fermions. I could actually do the same problem for bosons, but I'm going to talk throughout for fermions. And I will impose that the set of all jump operators is closed under Hermitian conjugation. As soon as you have this, it's a two-line calculation to show that this Lindblad equation takes a much simpler form. Yeah, so the dissipator part can be written as a double commutator, and this is basically then the key to everything that follows, because if I fulfill these requirements, you can immediately see this leads to closed equations of motion. Yeah, because this is quadratic, this is quadratic. Yeah, so if you calculate the in fermions, let's say, if you calculate the double commutator, the number of fermions I have in A of t, fermion operators doesn't change. Yeah, so therefore, if I look here at an operator involving n C's and C daggers, I will get on the right hand side only terms which involve exactly the same number of C's and C daggers. So in terms of Bogoliubov hierarchy, it means all the individual levels of the hierarchy decouple. Yeah? But unlike for free theories, they're all independent. Yeah? Whereas for free theories, they all follow from the first one. Okay, so this is some kind of new structure. So now we are not the first to do something about this. First of all, we noticed all of this and did some work of this 10 years ago with Maria Medvedeva and Thomas Brosen. And more recently, there was a lot of activity by various groups on specific models in different aspects. Jerome was one of the, well, you on that paper, unbeknownst to you. Yeah. Okay. Okay, but so the aspects I'm going to talk about, so the exact operator dynamics was not covered. So everything I've told you here actually works in d dimensions, but I will talk about d equals 1, and I can tell you later actually what becomes slightly more difficult if you go to higher dimensions. Now, let's be more specific. So we looked at a very large class of sets of jump operators. So I just show you 3 of all the ones we have done. So the Hamiltonian, we take always just a tight binding model. But now I'm going to show you results for 3 choices of jump operators. So the first one is just on-site dephasing noise. So this we studied with Maria and Tomasz 10 years ago. This is special for reasons I'm going to mention in a moment. Then the second model, we take jump operators that act across a bond. So that model is also very closely related to recent literature. So it's a generalization of what is called the quantum symmetric simple exclusion process. So this was introduced by Denis Bernard and Tony Jin. And it's a generalization in the sense they studied a purely dissipative model, only jump operators, so we add the Hamiltonian part. Okay. And as you can see, the jump operators are chosen in such a way so the rates are the same that the set of jump operators is closed under complex conjugation, Hermitian conjugation. The third model, so both of these models, model 1 and model 2, have a U1 symmetry, so particle number is conserved. So I want to contrast this to model 3, which breaks the U1 symmetry. So there I look at particle loss and particle gain. Okay, so, but the particle loss and particle gain is balanced because the rates I take to be the same. And then we have considered many others, so a lot of what I'm going to tell you you can do for other models, and the details look a little bit different, but the strategy is the same. Okay, now the trick here is these models, you can rewrite them, or the questions I've posed, you can write them in a way that a second-year undergraduate student can, well, maybe not a second year, but basically an undergraduate student can understand. Yeah, you can turn everything into a few particle problem. And this basically goes like so. So let's consider a general operator, psi hat, which is a linear combination of these bases of operators. Yeah? So this is the most general operator I can write. I've stuck here this stagger term for reasons that will become later obvious. Okay, so now the Lindblad equation in the Heisenberg picture, it involves a map of operators to operators. So it's convenient to vectorize this. So to use the fact that operators themselves form a linear vector space. So you rewrite them as vectors. So we call this vectorization. And the vectorization works side by side. On each side, I have four operators. I have the identity, I have C dagger, I have C, and I have C dagger C. Okay, so my vectorized space should be four-dimensional, and the way I can get this by introducing spin-a-half fermions. Yeah, because then I will have four states per side, empty, spin up, spin down, or both. Okay, and then the vectorization rules are like so. The identity operator goes to the vacuum state, fermion vacuum. The fermion creation operator goes to the state where I have a spin-up fermion. The annihilation operator goes to the state where I have a spin-down fermion, and then the number operator goes to this one here. So those are the vectorization rules. And if you use these, the equations of motion, which is d by dt operator is super operator acting on operator gives operator, turns into an imaginary time Schrödinger equation, very appropriate here for the ESI. So it's d by dt. This operator now turns into a state equals some pseudo-Hamiltonian times the state. And the initial conditions for this time-dependent Schrödinger equation are just given by which operator you're interested in. Okay? And just as a reminder, the number of C's and C daggers, they correspond to the number of downspins and upspins. Okay, so now these pseudo-Hamiltonians, for the various models I've written, you can just write them down explicitly. It's a very simple exercise. The first one, obviously, is my favorite. So that is the one-dimensional Hubbard model. And if you do it in d dimensions, you get the d-dimensional Hubbard model with a purely imaginary hopping term. Yeah? So it's not a Hermitian Hamiltonian because it's a Lindblad equation. It's a Hubbard model with imaginary hopping. So this we already studied and did various things 10 years ago. It's integrable in one dimension. Yeah, and it has actually an SO4 symmetry, but in particular, it has a U1 symmetry, which is what I'm interested in because I want to do hydrodynamics. The second model, so this generalized quantum SEP turns into this model here. Okay, so you again have just the imaginary hopping term. Then here you have a pair hopping term, and you have nearest neighbor density-density interaction. Okay, so this is this generalized quantum SEP. This model is not integrable, but still has a U1 symmetry. Okay, so now I have two models. Both of them have to show hydro. One is integrable, one is non-integrable, which was one of the motivations to look at this. But okay, the third model is more complicated and more interesting. So that was the one where I have particle loss and particle gain. So what do I have? I have hopping, I have density-density, nearest neighbor interaction, I have pair hopping, but now I also have quartet annihilation, yeah, if you wish, so something like this. And then I have one more term, which includes pair annihilation and something like C dagger CCC.
Fabian. So this is going back a couple of slides when you did, the vectorization.
Yes.
There may be other choices you could have done, like for example, you could have taken sigma plus sigma minus sigma.
Yeah.
And then you would have got some poly spin.
Yes. I mean, so I for reasons that will become clear again in a moment, I work with fermions. Yeah. If you work with spin operators, you get the same structure, but the precise questions you have to answer change a little bit, simply for the reason well, actually, for what we have done here, I could have rewritten everything in terms of spins. Yeah, but so there will be some questions for spin models that you then would want to ask, which are a little bit more complicated because they would involve a lot of fermions. Yeah, so.
Officially, you have this hierarchy should be closed, but this is totally not apparent when you get non-integrable model in the imaginary Schrödinger equation, or this is obvious.
Let me next slide. So you again, everybody is faster than the speaker. Okay.
So let me. So it's here. Yeah. So now what we want to do is we have vectorized the problem. So this is why I was saying, so now it's a very simple problem you can give to an undergraduate student because it's a Schrödinger equation with 2 particles or 3 particles, something like this, and they understand this and they can do it if they're motivated. So we want to solve the time-dependent Schrödinger equation as I have shown on the previous slide, and the way we do it is exactly like in quantum mechanics 1. We solve the time-independent Schrödinger equation and then use the eigenstates to write the solution to the time-dependent Schrödinger equation, and then we do asymptotic analysis on this sum. I mean, that's it. Okay, so now if I have now the difference between the U1 symmetric case and the case where I have particle loss and gain comes in. If I have the U1 symmetric model, I can write the eigenstates in a sector with fixed numbers of spin-up electrons and spin-down electrons. Yeah, so which means the equation of motion is just exactly at the same level. Yeah, so of the hierarchy. Whereas for model 3, again, if you think about it for a while, it's not surprising. It must have for the hierarchy to truncate, it must have triangular structure. Yeah, so which means the eigenstates, once I fix an up and n down, it can only involve states with at most n up and n down fermions or fewer. Yeah, and because of that triangular structure, you can always solve this. Yeah, because the problem with the hierarchy, it takes you off to infinity. So here it terminates. Yeah. Does that answer your? Yeah. Yeah. Okay, so now let's see how it works in practice. Okay, so you start with a single particle, but the single particle is extremely simple. You get a closed solution for the annihilation operator in momentum space. So you see, this is what comes from the tight binding model. This is what comes from the dephasing, and the dephasing basically just kills the operator at late times. So this is an exponential decay with a dephasing rate, and of course here there's no hydro, yeah, because it's in the one particle sector. And then this kind of structure that you have exponential decay of the operators in time continues for all operators with an odd number of fermions, and you can actually put some bounds on the decay rate. But okay, so as expected. In all of these sectors, yeah, operators just decay exponentially, and this is as expected because the hydromodes must be neutral. Yeah, the hydromodes of the particle number conservation U1. So, in order to get to the hydro, what we have to do is the simplest one. We look at the 2-particle neutral sector. And I'm going to show you, because it's my favorite model, how this works for model 1, but you can do exactly the same for all the other models, and we have done it. So if you're interested, I mean, I can tell you. So what you want to do is you want to solve the time-independent Schrödinger equation in the position representation in the sector where you have one electron with spin up and one electron spin down. That's a very old problem. So it was solved in 1967 by Flicker and Lieb, basically. For the Hubble model, and so what we do here is completely analogous, but I'm just going to take you through it. So this is the time-independent Schrödinger equation. Now, if the particles are far away from each other, the solution of this you can just read over just plane waves. Yeah, so you must have a plane wave when x is larger than y. You must have plane waves when x is less than y. Oops. And then when x equals to y, the wave function is allowed to jump because it's on the lattice. So this is the ansatz it works through. It works for all of the models. You supplement this by the boundary conditions. So let's say we are on a ring. So these are the periodic boundary conditions. And then what happens is the eigenvalues you can just read off. These are the eigenvalues. Yeah, it's given in terms of these single particle momenta. And then from the boundary conditions and the Schrödinger equation when particles sit on top of each other, you quantize the case and you fix all of these various amplitudes. So what we have is we have completely explicit expressions for all of these wave functions. And the quantization conditions for the K1, K2 are non-trivial because it's an interacting theory. So they take the form I've written here. There are two classes of solutions. Either the wave function is completely antisymmetric and the single particle momenta are free. Yeah, and what this corresponds to in the Hubbard model is basically you just start with two particle states in the sector with two up electrons which cannot interact, and then you use the spin SU2 to flip one of them, so you get these. Or in the other one, you have something like this, and the quantization conditions are written here, so it gives rise to this nonlinear algebraic equation. So these are equivalent to the Bethe-Ansatz equations for the Hubbard model. And in order to solve the problem I'm after, you basically need the solutions to all of these equations, plug it into the wave functions, and then work out what the wave function does at late times. Self-consistency. Where just a second. So, yes, at this level, so what you need to do is you need to diagonalize this Hamiltonian. Yeah, so I do it with coordinate Bethe-Ansatz because it's easy. If you want to do algebraic Bethe-Ansatz because you're a masochist, you're absolutely free to do it because for the Hubbard model it's very complicated, as you know, but you can. Yeah, but again, what I'm talking about here, all the other models are not integrable, but this, what I've shown you just here, it still goes through. Yeah. And the reason for that is in this two-particle sector, basically in one dimension, any model is integrable. Yeah, because you have two conservation laws, momentum and eigenvalue, and that's enough to enforce in the two-particle sector this structure of the wave function. Okay, this is terrible. Now, so let's see what the spectrum looks like in this sector. So for model 1, so this Hubbard model I was just talking about, all the eigenvalues are complex. So these are the imaginary parts of all the eigenvalues. These are the real parts. And what you see is most of the eigenvalues sit down here. They have a large negative real part, which correspond to states which decay very, very quickly exponentially in time. And then there you have one mode. This is a single particle mode where the real part at p equal to 0 goes to 0. This is your hydro mode. This is literally the hydrodynamic mode. So there it is. I mean, so you have it in its full glory for this Lindblad equation. And for this QSEP, generalized QSEP, you can do the same. And you see the spectrum, again, looks similar. Most of the states sit here. You again have a hydro mode, looks a little bit different. But again, there is some explicit wave function, if you wish. So those are the hydro modes. Oops, sorry. And for model 3, on the other hand, so there we broke the U1 symmetry. There shouldn't be a hydro mode, and this model, all operators basically decay exponentially. Yeah. And again, this is expected because there cannot be hydro. Good. Now, okay. So now let's do the hydroprojection. So how does that work? So we start with an operator of interest. So let's start with operators of this kind, because the most interesting operators, let's say, would be like density operators, if I'm interested in density-density correlation functions, or like C dagger x, Cx plus 1, so these kinds. And they're all covered here. So this is the operator I discussed now, so because it lives in this sector. Now, in terms of the Schrödinger equation, this specifies some initial condition, which I've written here. So I have to stick this extra factor, -1 to the j. This I stuck in so that in my Hamiltonians, the kinetic term is the standard kinetic term in terms of the spinful fermions. If I don't do that, the sign of the spin down hopping would be opposite, and you all would complain. So then what we know is the time-evolved state in terms of this effective Schrödinger equation takes this form, where the time-evolved wave function I can compute, as always in quantum mechanics, in terms of the energy eigenstates in this way. And okay, so I have this sum here, and this gives me the time-dependent wave function. I have an explicit expression. I will evaluate this for you at late times. But that then gives me these coefficients of the time-evolved operators at late times explicitly. So that solves the problem of hydrodynamic projection, in its full glory. So now let's do an example. Let's take this operator to be of this form, of course, which includes the density, and then C dagger j, Cj plus 1, C dagger j, C3 plus 2, so all of these. But of course, you can do much more generally, but I just show you the results here. And I discuss it for the two models that I've presented for you, where I have one symmetry where there is hydro, one integrable, one non-integrable. So notations, I define a capital X, which is the distance between these two arguments of the wave function, which correspond to the distance between the operators in the projection. And then x naught minus y naught is the size of the initial operator. Okay, and y is defined in this way. Okay, so now the upshot of this asymptotic analysis is the hydrodynamic projection at late times. It has this form. You can write it exactly in terms of some confluent hypergeometric function. So a fully explicit formula. The only difference between the integrable and non-integrable model is what you have here. This parameter alpha takes different values. Okay, so forget about the details. So there's a fully explicit answer in terms of some known special function. In a nutshell, what the hydrodynamic projection looks like is given here. So the wave function decay in time with a power law that has a very simple dependence on x minus y and x naught minus y naught. Okay? And this is the same in both of these models, and that's perhaps a bit surprising. To me, it's a somewhat surprising result because I don't understand where the structure comes from. So usually when you deal with hydrodynamic projections, you invoke symmetry arguments to project on the hydrodynamic degrees of freedom, and that cannot, I don't see how that can give you such a detailed structure. I mean, it's very difficult to understand. So physical explanation why you have this is not clear to me. I mean, just if x is y and x naught is y naught, so it's if you start with a density at time equal to 0, and then you look at the projection on the density at late times, that goes like 1 over square root of t, as you would expect. But then all the others, I have higher powers. Yeah. So Kurt will think about it. Yeah. Now, once you have this, you can try to do some more physical things. I have still a few minutes, no? Yeah, okay. So, now you can basically work out some physical properties of these Lindblad equations. It's very simple. So the first thing I'm going to show you is 2-point functions in the steady state. So the steady state in all of these models is very simple. It's an infinite temperature steady state. And the physics is you approach this state diffusively. And this is where the hydro comes from. And what you can do is you can look at susceptibility, so time-dependent, time and space-dependent 2-point functions in this infinite temperature steady state. So this would be the time-evolved operator I'm interested in. That's the non-time-evolved operator at a distance. And it's a trace because I'm in an infinite temperature state. And then I Fourier transform as usual. Yeah? And then I look at the real and imaginary part. So the imaginary part is the interesting one of this susceptibility. And so here are plots for the imaginary part of this susceptibility where I take the distance between these two operators to be 0. So I look at the density in particular. So this is frequency, this is momentum, and the color coding basically tells you how big the susceptibility is. And to cut a long story short, what you see is you basically see the hydro mode around Q equal to 0, as you would expect. And in the non-integral model also, but it looks a little bit different. So you can do other applications. You can ask, can I describe for this class of Lindblad equations pump-probe experiments? So it's a little bit more involved. So there, what you want to do is you want to do linear response after a quench. So the quench is the pump, yeah, and then you do the linear response measurement afterwards. So that's the probe. How to describe this in the Lindblad equation was worked out 10 years ago in this work. And so just because not many people know about this, I suppose here's a very brief review. So L0 would be Lindbladian time evolution. That's the kind of stuff I've been talking about. Now what you do is you add a very weak time-dependent perturbation on top, because you want to do linear response. And then now there are two time evolution superoperators. There is the full one, yeah, which is this one here. And there's the one of the unperturbed system. And because we're doing linear response, what you want to do is the linear response you want to rewrite entirely in terms of the unperturbed time evolution. Okay, what is linear response? So you look at the expectation value of some operator, yeah, in the time-evolved density matrix, time-evolved with a perturbation, and you subtract from that the expectation value of the same observable time-evolved with the unperturbed system. Yeah, so that's the change in the expectation value of the operator A due to the perturbation. And like always in linear response, you go through some algebra. You can rewrite it in terms of an integral over your parameter that parameterizes the perturbation and some susceptibility plus nonlinear response functions here, but we just do linear response. And the linear response function just has this form. Yeah, so it's kind of complicated. However, if you specify now, I want to do a Hamiltonian perturbation, so this L1 here I take of Hamiltonian form, which is what you would do in an experiment, then the susceptibility becomes a bit easier. So it takes this form, which is very nice, because what it looks like a dynamic response function, which is this part here, in the time-evolved state. So you evolve the state up to time t prime, and in that state, then you do a linear response measurement. So this is what this susceptibility looks like. And so in general, for Lindblad equations, there doesn't seem to be any work on this that I've been able to find, at least. Part of the reason is it's kind of complicated, but for these Lindblad equations we have here, they have a very simple structure. You can do this in its full glory. And we're just playing with this. I mean, you shouldn't take this too seriously. This is basically just a proof of concept. So what we do here is we do a pump where we boost the Fermi sea. I mean, so we basically start the free fermions in the ground state, and then we boost it. Yeah. And then we let it evolve in time, and then do the linear response measurement of the density operator after this quench. And this is the kind of susceptibility you get. This is the integrable model. This is what you have in the initial state for this susceptibility, and this is after time evolution. Anyway, so the last thing I want to say before I finish is, so I focused on the simplest operators, like density operators, quadratic in fermions, yeah, where you can do everything in its full glory. Well, of course, we have also looked at operators which are quartic in fermions, so this would be basically relevant if you want to compute a two-point function involving 8 fermion operators. Now, you can do an analytic analysis still for the first model using integrability, because the wave functions are very special. So the form I had written in terms of these plane waves generalizes basically to any number of particles. But this is no longer true for the non-integrable ones. And the reason basically is very simple. All right. So if you have some asymptotic region for particles, yeah, you have two conservation laws. You have the eigenvalue, so the quasi-energy. So that has to be fixed, and then the momentum. Yeah, and when the particles are far away, the wave function always is of this form: k1 x1 plus I k2 x2 plus I k3 x3 plus I x4. Yeah, but now these two conditions don't really fix the momenta completely any longer, which means there are many different plane waves in these different sectors which fulfill these conditions. And what the integrable model does, it connects precisely wave functions where these momenta are the same, whereas the non-integrable ones, they admix. Yeah? So what it means in terms of the operator evolution, the complexity of the time-evolved operators now differs in the integrable Lindblad compared to the non-integrable, and this was actually one of the motivations of the work to look at this, because I wanted to understand where does integrability really manifest itself in Lindblad equations, because there are no conservation laws like integral models have in unitary time evolution. Okay. But so what can you say? So for the integral model, there's still hydro modes, just in case you think, if I understand the hydro modes in the two-particle sector, I understand them area. It's not true. So here, I've plotted the hydro modes. There are two types of hydro modes. There again is a single particle mode, which is this one here. And we understand what that looks like in terms of the solution of these quantization conditions. So for the Bethe-Ansatz aficionado, so this would be a particular bound state. But then there are other hydro modes which form a continuum of states which correspond basically to scattering states of the kind of states I had constructed in the two-particle sector. And this can be made precise. And that one has some structure like this we had already, in general terms, noted 10 years ago. So here's my summary, and I'm on time. So the main message is, so there are many particle Lindblad equations with decoupled hierarchies for which detailed aspects of diffusive dynamics can be worked out exactly. And so what we have done is we have exact hydrodynamic projections for all operators quadratic in fermions. Using this, you can model, again, for this class of Lindblad equations, for example, pump-probe response functions. And one thing we're thinking about at the moment is to quantify, in terms of some measure, the difference in the operator complexity between integrable and non-integrable equations in this higher particle sector. So the thing I just described here. And with that, I thank you for your attention.